In this video, we will be solving a few problems on first-order linear systems. So let's have this example. Basically, in this kind of lesson, we have this form, x prime is equal to ax plus b. If b is equal to 0, then this is nothing. We are left with this, and therefore our equation is homogeneous. So you have to recall your differential equations, no? So if b is not equal to 0, then we can say that the equation is non-homogeneous. So one thing that you have to know is that the x here, the a, is gonna be our matrix, no? There are formal terms for each variable that you see here, but I just want to shotgun the way. Basically shotgun the lesson to you. I'm not gonna go through the formal way anymore, basically. So for the matrix, how do we form it coming from this problem? So we have xyz, no? xyz. X prime, we rewrite this as dx over dt, dy over dt, and dz over dt. Okay. Oh, by the way, it's important that you are knowledgeable about matrices before proceeding to this lesson. It's very crucial. So basically, I'd look at the coefficients of x, y, and z for each of these, and yeah, just list them as a matrix. So x, y, z. And here we have the coefficient of x is 1. For y, it's 5. For z, it's -1. Here, there is no x. So we just put 0, no? 0, and then y is 1. Z is -3. So this is the matrix that we established. And then put x. As you can see, there is no constant, no? There are just variables. Therefore, in our case, right now it is homogeneous. So what's the first step? Now that we have this, so we have to pay attention to our A, our matrix. The first step to evaluating is by this. So basically, what that means is you don't have to mind the I anymore. The summary of this concept is that you basically place in this matrix a minus m in the main diagonal, no? Main diagonal, it's this one always. In a 2x2 matrix, let's say this one, I just took this, placed it here. The main diagonal is this one, no? So if we apply this, the first step, we just put -1 on the diagonal, no? So okay, so that is, 5 minus m. That's what we have so far. Then write c1, c2, c3, then equal to 0. -4, -1. Right now, we have to look for something that's called eigenvalues. So since this is a 3x3 matrix, it's done this way, no? So -4, -m, then just write this. This one, the one here, what's not part of what I wrote or what I crossed was this and this. So that's what I put here. 1, 1, 1, negative 3, negative m. Okay? And then plus 0. Again, it's important to learn your matrices because it's going to be much easier to understand what I'm doing. I'm not going through the specifics anymore. The multiplication, scalar in vector, in matrices 2 by 2, 3 by 3, etc. Okay, also the array of signs, plus, minus, plus, minus, plus, minus, plus, minus, plus. So how is that applied here? As you have noticed, probably, here, it's positive, no? We just copy the negative from this one itself. In 1, we put a minus. It's this one. In 0, that's still a plus. Shortcut. For as long as you see a 0 here, this entire thing is 0 already. So it's as if you didn't have to write it anymore. Okay? So now we multiply 5 minus m times negative 3 negative m plus 1 minus 1 negative 3 negative m minus 1. Okay. Essentially, everything here, the entire process is tedious, but it's not so hard. Negative 15. Remember your FOIL method. Minus 1 times quantity. Okay, and then don't forget the equal to 0. This is quite a lot of, I expect like around 3 eigenvalues. I hope we can just plot these in the calculator. Let's see if it works. Okay, negative 4 is one of them. So apparently the calculator can look for one of the values, but not everything. Past the algebra, we get eigenvalues of negative 3, negative 4, and 5. Like I said, this is a tedious process. We're gonna evaluate each eigenvalue. Go back to this one. So it's already no longer a mystery, no? What m is. We just substitute. Okay? Negative 4 minus negative 3, that's negative 4 plus 3. Copy the rest. Negative 1 and 1. 5 minus negative 3, that's 8. Negative 3 minus negative 3, that's 0. Sorry. We're not supposed to put C in this part of the solution. It's supposed to be written like that, with the absolute value sign. The only time we put C1, C2, C3 is when we evaluate, no, for each eigenvalue. Okay, so negative C1. Remember, row, column. Okay, so negative 1 times C1, and then C2 times 1, C3 times 1. Okay, next C2 plus 8C2 minus C3 equal to 0, and then C2 equal to 0. Okay, so that's pretty direct. Let's narrow it down. So negative C1 plus C3 equal to 0. Sorry, this is supposed to be C1. C1, this one is going to be 0, no? So minus C3. Technically, they're the same. So let's just assume if C1 is equal to 1, then C3 is also equal to 1. Now, we have established that basically this one, the C1, C2, C3, is this, no? For m is equal to negative 3. It's 1, 0, 1. And if we want to make the equation, so we'll label this as x1 equal to c1 times 1, 0, 1 e raised to mt, m being negative 3. So e raised to negative 3t. Okay? And then for m is equal to negative 4, let's repeat the process, no? Again, let's look back at this. So substitute negative. Okay. 1, and then 0, 5 minus negative 4, 9, 1, 3, negative 3 minus negative 1. Sorry, not absolute value. Parentheses. Okay. Let's just rewrite this as 0 na lang. C2 plus C3 equal to 0. C1 plus 9C2 plus C3 equal to 0. C2 plus C3 equal to 0. I hope you see the pattern. So technically they're the same. I need to write the second time. So what can we do now? C2 is equal to negative C3 transpose. If C3 is equal to 1, we can assume any number, by the way. But to make things simple, either 1 or 0. 0 if applicable, no? How do you know if you can substitute 0 to a constant? Constants being C1, C2, C3, or P1, P2, P3. So I'm mentioning the notations now, so that you will be expecting. Normally, it's okay to just assign it to a value of 1. That is, if you're playing it safe, no? But we can be smarter, and for as long as our vector is not going to end up with 0, 0, 0, it means there's no direction. So if we end up with that, don't use 0. But usually, because in this case, this is real and distinct eigenvalues. Why? Because these values are distinct. In other cases, complex eigenvalues, we have, for example, 2 plus minus 2i, the one with I, coming from this form, no? That's actually case 2. This one is case 1, real and distinct eigenvalues. Case 3, the last one, is real and repeated, not distinct. For example, we have negative 2, negative 2. So they're repeated. Particularly in this case, I'd like to mention that when you are evaluating the eigenvalue for the second time, I think it's safe to assign a constant to 0. I understand that it's hard to visualize it right now. You don't really have to know about that for now. Let's go back to our lesson. to our focus. So if C3 is equal to 1, C2 is equal to negative 1. Okay? So now that we've established that, again, we can assign any number. It's very much safe to do, to assign any number. But yes, again, to make it simple, just assign 1. Okay? So C2 is negative 1, negative 9 plus 1 equal to 0, C1. Negative 8, C1 is equal to 8. Okay, C is equal to 8, negative 1, 1. Is that the case? Let me confirm if what we're doing is okay so far. Hold up. My bad. You see the negative 1. It's supposed to be copied. So from there, this is supposed to be minus. So negative 10, positive 10 is C1. Okay, so far so good. Wait, let me double check. Okay, so far it's okay. So we're gonna label this as x2 equal to c2, and then our second vector e raised to mt, m being negative 4. Okay, now for m equal to 5, sorry, negative 4, negative 9, 1 0, 1 1, negative 1 1, 5 minus m, 5 minus 5 is 0, negative 8. Okay, c1, c2, c3, and then 0. Negative 9 c1 plus c2 plus c3 equal to 0. c1 minus c3 equal to 0. We can say c1 is equal to c3. c2 minus 8c3 equal to 0. c2 equal to 8c3. So let's bring this. Let's assume c1 is c3, no? Substitution. And then the c2 here is gonna be 8c3. Let's see what happens. 9, 18, 9. Huh. We can't say that c3 is 0. I think let's just stick with this condition. So if c3 is equal to 1, c2 is equal to 8. And c1 is equal to 1 also, because of this. Okay, c is equal to 1, 8, 1. x3 is equal to c3, 1, 8, 1, e raised to 5. Okay, so now that we evaluated each eigenvalue, our general solution, usually we're given a boundary condition, no? values of x and t. But in this case, we are not given any information on it. So we just express our final answer as the general solution. That is x1 plus x2 plus x3. Okay. So that's basically it for this video. This one problem, it's pretty lengthy, no? So yeah, that's how you solve first order linear systems. Case 1, real and distinct eigenvalues. Bye-bye.